Okay, so here we are on a Wednesday, so we're working in Chapter 7. So Chapter 7 was the analysis of the Group 1 mechanisms. I guess for administrative stuff, there's a homework out there for Chapter 7. I forget what the due date is, but it's not anything immediate. And then after Chapter 7, we have the second exam. And we've got that right now set for Friday, November 8th, if I remember right. And it'll be pretty much run like last time, so the people that are in the online section will all pile in here. And there's a lot of the old exams are out there, so you'll be able to take a look and see what we've got. Oh, Friday, again, I'm going to do basically I'm visiting with family. And so I'm going to make a video tomorrow, and I'll link it to our class webpage. And it might be in Chapter 8. I might make it all done with Chapter 7 today. So in Chapter 7, what we ended up last time was, and there's one little comment I wanted to make on this one that I forgot to, but we were working on, again, analyzing Group 1 spatial mechanisms, and this is one of the ones that we did. So it's kind of shown over here. Here's a nice 3D mechanism, and the main criteria we have was that this better be 1 degree of freedom. So again, if you add for the closed loop, if you add the freedoms of the joints -6, it gets you the mobility. And it looks like we've got 1, 2, I'm counting the revolutes, 4 revolutes and 3 prismatics. So 7 minus 6 is 1. So we definitely have a 1 degree of freedom mechanism. And then we drew the equivalent spherical mechanism. And on that one, because of the prismatic at 5, I kind of showed that as like it was welded. In other words, I know that joint angle. And also the prismatics were at 2 and 3, so I know those. So I said, well, I might as well like weld a piece of metal across there to indicate that. So if we look at the mobility of the equivalent spherical mechanism, it's, again, with the closed loop, it's the sum of the freedoms of the movable joints -3, and there's 4 movable revolutes. 4 minus 3 is 1. So we have a 3D spatial mechanism whose equivalence is 1 degree of freedom, whose equivalent spherical mechanism is 1 degree of freedom. So that's why it fell into this chapter. And then the particular problem that we were doing with this was, and my computer's being a little persnickety today. Particular problem was this. So this is the planar representation of that fancy 3D picture. So it's kind of indicating where the prismatics were. And so in our problem statement, we know all the, for the 3D spatial mechanism, all the twist angles and the link lengths. So all those pieces of metal, we know everything about them. And then there was a revolute at 1 and a revolute, back off of that. Oh yeah, it was a revolute at 1, so we know that joint offset. There was a revolute at 4, 6, and 7. So that's why we know those offsets. And then there was the prismatics at 2 and 3 and 5. So that's why we know those. Again, 1 degree of freedom device, boom, we gave you one of the angles. So we did this last class, and what we found out of this was for that theta 7, we had an A case and a B case. We were able to get theta 1A, theta 4A, theta 6A, and then where the prismatics were S2A, and then 3 and 5, and then there was a B case. So the thing that I forgot to mention is what's one way that you can check your answers, so you know if you got the right result. So once I know for the A case all of the parameters now, I could go ahead and build this matrix, the transformation 2 to 1, right? It depends on theta 2 and alpha 1, 2, and A1, 2, and the S2 distance. And I know all that now for the A case and for the B case. And I could get this matrix, and I could get this matrix, and I could get this matrix, and I could get that, and I guess there's 7 to 6, and I can get 1 to 7. I can get the relationship because it's a closed loop mechanism. So if I go ahead and evaluate all of those for the A case, and I multiply them all together, I better get the identity matrix, right? Because 7 cancels 7, 6, 6, 5, 5, 4, 4, and I get transformation matrix 1 to 1. So that's the check. That's what I forgot to mention last class. How we can tell if we got the right solutions for that. Let's see. Okay, so what are we working on today? Let's skip down to here. So this is going to be the first day that we do actually a reverse analysis. That's what we're really trying to get to. And this one that we're going to do right now, I did not put in the text, and I wish I would have put this as the first one in the text, because there's not going to be any strange things happen with this one, and you'll see what I mean by that when we do the next one. So I've got this mechanism, and I'm going to look at it. It's got a revolute, a prismatic, revolute, prismatic, prismatic, revolute. So I look at the mobility of it, and again, in an open loop chain, the mobility is just the sum of the freedoms of the joints. So I got one freedom relative there. There's another 1, 2, 3, 4. So it's a 6-degree freedom manipulator. You say, okay. For the reversal analysis, let's go ahead and look at the problem statement. For this particular mechanism, what are the things that are never going to change? That's our constant mechanism parameters. So again, for the links of 1, 2 through 5, 6, I know everything about those. Let's see, there's a revolute at 3. There's a prismatic at 2, 4, and 6. I'm sorry, 5. 2, 4, and 5. So I'm going to know those joint angles. And then you say, well, yeah, there's a revolute here. How come I don't have an S1? And it's because that's, remember, the first joint where we go relative to that fixed coordinate system. You know, there is no S1. And again, the S6 is not exactly a constant that never changes. It's a user choice to establish that last coordinate system. So for our problem statement, boom, that's the stuff that we know that never changes. And then what did we do? We needed to, oh good, I accidentally went to this slide, but we needed to establish the coordinate system on here on this last body. This last body is like the mounting plate usually of the robot. So I need to pick a distance S6. So, for example, that sure, I can see the S5. I bet you that's my A56 vector. So how far do I walk from A56 along S6 to get to where I want to put the A67? I usually pick the distance that'll put that A67 line on the mounting plate, but you don't have to. And then on the mounting plate, we're going to etch that direction so that I can, because now the last coordinate system, I can see it. It has Z along S6 and X along the A67. And again, this isn't anything new. We did this when we talked about the manipulators and did the forward analysis and all. There's our stuff that never changes. We made this choice of S6 and we etched that direction so we get that coordinate system on the last body. Then in the reverse analysis, we're going to basically, it's like, what's the desired position orientation of the last body? I skipped the tool part here, because previously we would have said, oh, there's a tool point known in the 6 coordinate system, and I'm going to say where I want that in the fixed. And what's the first thing we did, right? We just went ahead and calculated that. So I just said, Matt, that's given now. So I'm going to tell you where I want 6's origin to be, so that's that point right there in the fixed. And I'm going to tell you the directions I want for the Z and the X of that coordinate system in the fixed. So that's my desired position orientation. And then here's the variable joint parameters. So phi1 is because of the first revolute. Yep. S2 is prismatic. Theta 3 because there's a revolute. S4 was a prismatic. S5 was a prismatic. So this is our first, real reverse analysis. And then, wow, I didn't even put it in the book. Okay, so what's our first steps? Okay, first thing we're going to do is make these 2 free choices to establish an S7 direction. Or I should say more than a direction, it's actually like a line that it's along. Because and again, we didn't have to pick these values, but when I did those values, it turned out that the S7 line was going to be along like the negative of the Y6. You know, it's like put your thumb along S6, and then am I going to get this right? Oh, I'm sorry, alpha 6, 7. Put your thumb of your right hand along A6, 7, and I'm changing pages when I'm trying to draw. Right? What does alpha 6, 7 means? It says put your thumb of your right hand here. Start your sweep at S6, go 90 degrees, so the S7 would sort of be down, trying to get it perpendicular there. So we make those 2 free choices, and the fact that the A67 distance is 0 means that that S7 line is going to go through 6's origin. We could have made any choices we wanted there. Those are easy choices. What I like about it is sines and cosines of 90s are going to appear in equations, and they go to zeros and ones, and it's just like. So that's our first step. And once we've established that S7 line, then we're going to close the loop. So the S7 in this case, probably I could draw it better on here. It's sort of going to be down that way. I'm trying to get it perpendicular to, to the S6. And then we're going to look at the S1 line and the S7 line, and we're going to find this unique perpendicular. And for that perpendicular, right, we're going to make our choice of A71. We'll know it in the fixed, and then we're going to get three distances. You know, all the stuff we did when we closed the loop. So basically, we're taking this reverse analysis problem, and we're turning it into this closed loop mechanism. And what we're going to find is that this closed loop mechanism is going to have 1 degree of freedom, and one of the parameters that we calculate when we close the loop is theta 7. And then when we look at the equivalent spherical mechanism of this, it better have 1 degree of freedom also, or else it wouldn't be in this chapter. Okay. So hopefully, I said the story I'm telling is like, yeah, we've seen this stuff. I kind of see what's coming. Okay, we close the loop, and once we've done the closed loop setup, we are going to have a closed loop mechanism that is 1 degree of freedom, because we have, there's now in the closed loop mechanism, there's 7 joints, and they're all either revolutes or prismatic. So 7 minus 6 is 1, so the freedom of the closed loop is 1. And then we generate this table. So this sort of salmon color, those were the constant mechanism parameters. This is the free choice that we made to establish the coordinate system on the last link. This is the free choices we made to get the S7 line. And then when we close the loop, we got 3 distances and 3 angles. So there's a distance, there's a distance, and there's a distance. And then the 3 angles were alpha 7, 1, theta 7, and then the gamma, which is used at the end. Because when we analyze the closed loop mechanism, we are going to get theta 1, but what the robot really wants was phi 1. Okay. So we're just trying to emphasize from this table that at this point we have a closed loop mechanism where I know all the A's, I know all the alphas, I know one of the thetas. Where the revolute joints, I know their offsets. It's ready to go. It's good to go. So now we're going to analyze the closed loop mechanism, and we're going to calculate these yellow parameters, because there's 3 prismatics and 3 angles. And then once I get the theta 1, there'll be an A and a B case. I'm going to use the gamma to get the phi 1, A and the B case, which is what the robot wants. But all these other parameters are ready to go. The robot will be happy with those. Okay, so here's the planar representation of the spatial mechanism, and this is the planar representation of the equivalent spherical. So you can see where the prismatics were at 2, 4, and 5. We went ahead and just kind of, those angles are known, so I just kind of marked them off like that. So let's go ahead. I'm going to draw the second one, the equivalent spherical mechanism. 1, 2, 3. And I'm going to say, what angles do we know? And let's see, there was a prismatic at 2, so I know that one. There's a prismatic at 4 and a prismatic at 5. I know theta 7 from close the loop. So again, whenever we analyze a group 1 mechanism, I say that the solving for the joint angles, it's decoupled from solving for the 3 joint offsets. In other words, we're going to be able to solve the joint angles by looking at the equivalent spherical mechanism. So the 3 joint angles that we need to get are theta 1, theta 3, and theta 6. It's just a matter of who do we want to go for first. If I go for theta 1 first, then I'm going to look at the cosine law that'll get me that. So it's going to be z, and I'll say 7 is okay. I don't want to put 6, right? I'm looking for 1, so it's okay to put 1 in the equation. It's okay to put 2. Oh boy, I don't want to put 3, right? Because I don't want theta 3 in the equation. So I stop and say, well, to get a fundamental equation, I'd have to have 5 subscripts, and I only got 3, so I know it's a subsidiary cosine law. And if we look in the book, Z12, and I go step, step, it's going to be Z54. And to me, it's kind of the power. It was a pain in the neck generating those toolboxes, but holy cow, once I got them, I don't have to prove out all those equations. I know they're valid equations. And to me, I just like to say that this equation for this problem, when I drew this picture, just jumped right off the board at me. Now, granted, it's open book, and you got the appendix, and you can look down and say, can I find an equation where theta 1 is the only unknown? Or another way to say, can I find an equation that doesn't have 3 and doesn't have 6? And you'll find it. That's the one. So we know what to do with this. Theta 1 is the only unknown, so we need to expand this. So Z712 is, I always have to stop for a second, it's a sine XS plus YC plus a cosine Z, and I'm going to say minus Z54 equals 0. So I know that's a valid equation, and then I have to say where X71's definition, and then I got to be careful, there's no bars here, even though, because it's 7, 1, 2, 3, I'm going uphill, is that, and Y71 is cosine XS plus YC minus a sine Z, and Z71 is a sine, then the same XS plus YC plus a cosine Z. And here's our unknowns. So we have to substitute that up there and regroup and all, but what we will get if we do it correctly is we'll have A cosine 1 plus B sine 1 plus D equals 0. So for example, the A term was going to be S23 X7S2, so I'm substitute that up there and grab that. Yeah, I guess I could write this one down. The A would be S23 X7S2. And then when I substitute this up here, I'm going to get a plus S23 C12. I'm going to mess this up. X7, no, sorry, Y7, because we're grouping the C terms. Times C2, because of that. And then I have to substitute this up there and add in a, C23 times, here's the term, S12 Y7. So if I grouped it correctly, everything that had C1 in it, that's what you would have. And the reason I wanted to write it down is I wanted to make sure that you're okay, that based on what we're given, that's going to turn into a number. Because I've got alphas are all known. Theta 7 is known, and there's alphas in there. Theta 2, there was a prismatic, so I got that. Again, alpha, alpha, theta 7, and a bunch of alphas. I got all that. Theta 2 is given. Yep. On the D term, you're going to have the, similar to that, but you have the Z54. But wow, those theta 5 and 4 are both known, and a bunch of alphas. So they will all, again, the ABD will turn into numbers. So at this point, we would say for this mechanism, I've got a theta 1A and a theta 1B. Then it's a matter of going for the other joint angles 3 and 6. And we know that it's not going to double up. There's not going to be a theta 3A1 and a theta 3A2. There's going to be a unique theta 3 that's going to go there. And that means we need to get the sine and cosine of theta 3, which means we need to have two equations. And we can go in the toolbox and dig around and find a whole bunch of stuff. But boy, this buddy thing just always works. So I get lazy and I just do it. I said, that equation was so good to us. Let's look at those. And they're going to be good to us also. There's not enough subscripts to be a fundamental. And 712, when we go into the, we'll double check this one, but it's going to be 456. And let's make sure I got that right. I'm going to open the appendix. That'll take 2.5 seconds. Well, maybe. So I go book, and I got an appendix. Yeah. Open with that. Well, what do you mean? Why is it asking? Okay, and we're going to go near the bottom because we're in the 7-sided. So we go down, and Okay, so here's the beginning of the heptagon, the seven-sided. So here's all our fundamental formulas. But we're looking for x712 and y712, and I go down into the subsidiaries. And holy cow, there's a lot of equations, but hallelujah. x712. Oh, wait a second. Oh, I did make a mistake. I'm glad I checked. Yeah, I went the wrong way. Glad I checked. The way that I remember it is 712. I remember the z was this. I have to go 543. So good thing we checked that one. Okay, and then I look at that buddy equation and said, how's that going to help me? It turns out it's going to get me theta 3. So if it's going to get me theta 3, we need to expand these definitions. I'll have x54c3 minus y54s3 is equal to x712. I'm going to put this minus sign over on this side, minus 712, and expand that. xs plus yc. If that's my two equations, two unknowns, then for the A case, I better know everything else is numbers. That's got theta 4 and 5 in it, and a bunch of alphas, and theta 4 and 5, there's no A or B thing, they're given. So yeah, those are numbers. Over here, I'm gonna take theta 7. Oh, I'm gonna have to take theta 1A. And then theta 2 is given. So for the A case, the right-hand side, I'll evaluate to numbers. Solve two equations, two unknowns. I know the sine and cosine. If I was writing a program or doing this in a problem, I would probably stop right now and I would take my two solutions, S3 and C3, and I would square them and add them together and see if they went to 1, because if they didn't, I've got a mistake somewhere. Then we're going to take these same two exact equations. These are not going to change in value because theta 4 and 5 are the same. But for the x712, y712, I'm going to put in theta 1b. I'll get new numbers here. For the B case, I solve for the sine and cosine. So again, I didn't have to use those buddy equations, but boy, they just always work. Then we have one angle left, is theta 6. So what I said, well, I know the definition of Z712 is the same as Z217. So let me look at those. And boy, this time I'll try not to mess up. 217 is going to be 456. Wow, that's going to allow us to get theta 6. So we're going to expand x456, x45c6 minus y45s6 equals x217. I'm going to put the minus sign over here, minus y217. We're going to expand that. xs plus yc. Wow, two linear equations and two unknowns. Again, theta 4 and 5 are given, so those are going to evaluate to numbers. Over here, theta 2 and 7 are given, but I'm going to take theta 1a. For the A case, I've got two equations, two unknowns. I get S6 and C6, and I get the unique theta 6A case. Take the same exact equations, but put in theta 1b. Solve the two equations, two unknowns. So now those steps of like taking those numbers and evaluate them, if you're doing it in a program, you got a lot of typing to do. But it works. So in our problem statement, we've done all we could with the equivalent spherical mechanism, and what's left for us to get are the the slider values for the prismatics. That would be the joint offset S2, S4, and S5. And here we go. The S1 distance times the S1 vector plus the A12 distance times the A12 plus the S2. And I'm going to go plus dot, dot, dot plus A67 plus S7 plus A71 equals the 0 vector. So there would have been 14 terms, and my chalk's getting pretty short here, so didn't write them all out. And then to solve that, it turns out that there's three distances that we don't know. One of them was S2, and the other ones were in the dot, dot, dot. I didn't write them out. So to solve this, we have a couple of choices. I could evaluate all the vectors in a common coordinate system, and there's 14 of them given in the appendix. And all of those vectors, because the joint angles will know, I'll get, you know, the direction, the three components of all of those vectors in that coordinate system for the A case and the B case, and I can solve three equations, three unknowns. Or what I might do on this one is, because 4 and 5 are next to each other, I might take the vector loop equation and dot product every term with A45. And then I'll get a scalar equation. I'll get one equation in the unknown S2. And then I'll have to go back and do another dot product to get another equation. But there's, I mean, solving, whether you solve three equations, three unknowns, or you do it with the dot product thing, it doesn't really matter. You get the same thing. So the homework problem that you have over here is, it depends how I write the test, but it was an old test problem. And if you look at a lot of the old test problems, a lot of them are like the homework problems. I call them engineering essay questions. So it depends what I give you. If I give you numerical stuff, it takes like forever, right? And it's easy to make a mistake. And to me, what's more important was the big picture. So what I just did here was the engineering essay question solution. For example, I said, oh, I'm going to start off, and I decided to go for theta 1 first. I use this equation. I can factor it into A cosine plus, and in other words, you're telling the story. And then he said, oh, then I decided to take these equations, and when I expanded that, and what's tough with the engineering essay question is you never know, well, how much do I have to write? So let's look at an example of one. How much do I have to write to convince me that you know what you're doing? Which is a fair question, and I honestly don't have an answer. But if we look at some of the old exams, when I looked the other day, I think there was only one exam where I had you do numerical stuff, and I'm like, oh my goodness. So let's look at last year. Skip that one for now. Yep, here's an engineering essay question. Accompanying figure shows a planar representation of a spatial mechanism. So that's the planar picture of the 3D. It better be a group 1, right, or we're on the wrong test. So if you look at the mobility of the 3D mechanism, the sum of the freedoms of the joints, right, they're all 1 degree of freedom except the, see if it'll let me draw here, right, except for that guy. So you add up, there's 5 of them that have 1 degree of freedom, there's one that has 2, so that adds up to 7. 7 minus 6 is 1. When we go to the equivalent spherical mechanism, let's see, we're going to know that and that. Okay. Well, let's see what the question says, but I am going to know those two thetas. So the first thing this engineering essay question said, explain what group mechanism it is. All right, it's a 1 degree of space. It's a spatial mechanism that's 1 degree of freedom, whose equivalent spherical mechanism is also 1 degree of freedom. And there's a percentage of class that aren't able to say that. Right? You got to make sure you know why we call them group 1. They're always going to be 1 degree of freedom, 3D spatial. It just happens that its equivalent spherical is also 1 degree. Oh, list the constant mechanism parameters. What are the things that never change over here, right? Those two thetas, those offsets when, oh, I got a typo here. My goodness. An A61. So I always hate it when because I put the solutions out here because there's just, the old exams will live on and be findable or whatever. So I put these out here to be a study aid, and it doesn't help when I make a mistake. And what happened is I cut and paste from a previous exam that only had 5 links. So I better fix that one. Okay, so I didn't get full credit today on part B because I messed up that there were 6 links. Okay, what does this next one say? It says, assuming the values for all the constant mechanism parameters are known together with a value for, oh, I gave theta 5. Explain how to get all the possible, oh, for S4. That's kind of a loaded question. Basically, I'm surprised I didn't like step you through the whole thing on this last year. Basically, you got to solve the whole problem, right? I got to get the A and the B case angles, and then I got to do 3 equations, 3 unknowns. That's how I'm going to get S4. There's not like I'm magically going to write an equation that has theta 5 as the input and the constant mechanism parameters, and S4 is the only unknown. So I basically even got lazy when I typed it out here and just said, basically what I said is solve for all the stuff. Okay, so how did I answer this as far as an engineering essay question? I said, well, there's 3 unknown angles. 2 unknown angles. I'm given 5. No, I guess 6, 1, and 3. Oh, right. Oh, yeah, so there's 3 unknown angles. Who do I want to solve for first? It was my choice. I decided to go for 6. So when I look at this equation, again, it jumps off the page. Z4, 5, 6 equals Z2. Made sure that was in the appendix. I expanded it. I said that can be factored like that, where A, B, and D. And then I just said, I know I'm going to get 2 answers. So when I did this, if this was the engineering essay question, I was doing the tests, and this was turned in and it was graded, I would say, it's obvious you know what you're doing. You don't have to go in and reprove how do you solve A cosine plus B sine plus D equals 0. I mean, you get it down there and say there's 2 answers. That's it. That's fine. Then I said, well, I needed to get corresponding values for the other angles, so I used these buddy equations. This is just what we did on the board. I even moved the minus sign to the other side. And then I said the given mechanism parameters, the input angle and the value theta 6a are substituted in these equations to get the sine and cosine of theta 1 for the A case. Equations are used again with theta 6b to get the sine and cosine for the B case. Thus, unique corresponding values are obtained. That is theta 1a, theta 1b. Then I took these equations. I probably cut and paste that paragraph and changed the names to say how you got, oh, they were fundamentals. Shoot, boom, boom. There's sine and cosine right there. And then to get those 3 offsets, oh, I didn't write a ton here. I said value for the 3 unknown offsets. I said, well, I'm going to take this vector loop equation and then engineering essay question. All the vectors can be expressed in the same coordinate system using the A case calculated joint angles. This will give 3 scalar equations solved for the A case offsets, S1A, S2, and S4. Then the vectors are next evaluated. Now, what's weird is, you know, it is kind of weird, but it's legal in a way, but I'm thinking about it. If I asked a similar question like this and you got to the end and you wrote, right? You cut and paste this paragraph and changed all the letters, it's correct. And I'm not going to claim that you just copied or whatever. You're just expressing that you know what you're doing. So again, the engineering essay question, you don't have to calculate. I'm not sure what I'm going to write up yet, but this is what I did on most of the exams. I didn't feel that there was anything to be proven that much to have you put numbers in and evaluate everything. It's much more important that you see the big picture and can explain how you solved it. So the only thing I did on that assignment was, instead of on previous tests, you'll see, I'll say part C, you'll say, tell me how to get theta 6. And then I'll say, tell me part D, tell me how to get the corresponding theta 1. And then how do you get, and what I did this year is I just said, oh, how would you get the 2 values for S4? Well, yeah, you got to solve the whole problem. Okay, so that's an example engineering essay question, which is what I've been doing on the board, just talking through it. Okay, so we got 20 minutes left. We're going to do one more problem, and because we're going to find that all of these group 1s are so easy based on what we did in chapter 6. Because you're going to be able to get the A and B case joint angles directly from the equivalent spherical mechanism. We get the next chapter, so let me put this one away, and we're going to go ahead and look at what I did put in the book. So I wanted to do a reverse analysis, and I said, oh, this is going to be the simplest mechanism. Because basically the equivalent spherical mechanism when you close the loop is just going to be a 4-bar. So right, we're going to have like Z41 equals C23, you know, Z. So I said, oh, I just want something easy. But when I introduced this, what's different is the first joint is a cylindric, and that made something a little different. And I would have been much happier if the one that we just did in class was in the book first, because you feel kind of cozy and comfortable. And then you see a little weird thing, then it's okay, but I didn't do that. Okay, so when we had a revolute at the first joint, we always said that the origin of the fixed coordinate system was at the same as the location of the first coordinate system, and that's not going to be the case here. I can see the fixed, what I picked, but the first has the origin at the intersection of the S1 and the A12 line, and the Z of the first is here, and the X of the first is there. So by putting a cylindric as the first joint, I'm like, oh, great. I've got something a little bit different. So I called this distance L1. So, and when we do the reverse analysis problem, where we're going to look at what exactly are we given, what are we looking for, but L1 is one of the things we have to solve for. So it's like, oh my goodness. So we have something weird over here. And it also feels a little bit weird because when we did all close the loop, we always said, let's find the imaginary S4 line. I'm sorry, S7 line. But on this one, it's going to be the S4 line. So the numbers all change. Okay. So what's our problem statement? First of all, you said, wow, that's all I know? Those are the things that never change? Because, yeah, there's a piece of metal here and there's a piece of metal there. Those are the only things that never change. And then I said, the third coordinate system, I can see it now. There's the Z. And in that body, of course, this body is sliding along here. So I don't even remember how we had S6, because there was always a revolute at the end, because on the real robots, it's usually just a revolute with a mounting plate. So the other end is a little different also. This joint offset value, right, is a variable, right? Because this joint can slide and rotate about that axis. So it turned out that's all I know. And then, again, I got the tool point in the third. Where do I want it in the fixed? And then I'm going to say I want to specify this guy and that guy in the fixed. And the first thing we're going to do is take all that information and get, in this case, it's 3's origin. So I'm going to be able to say I want that point. Let me change color here. We're going to say I know this point where I want that to be in the fixed, and I know that direction and that. So I know, basically, I know this, 3 to fixed. Okay, what are our unknowns? Well, for the first joint, I need to get phi1 and L1, right? Because L1 tells me how far I got to slide that thing up from the fixed coordinate system. And then for the other joints, theta 2 and S2, because it's a cylindric joint, and for the third one, boom. So here I go to do the first reverse analysis that's in the book at all, and I've got something, I got a cylindric here, which made it kind of weird, and I got a cylindric here. So we're not able to say, oh, pick S6 and etch the line. No, I etched the line in that body and found out where the origin was in that body, but then that is is a variable, is an unknown. So here I try to do a simple one, and I kind of have weird things happening on both ends. Okay, so the front of the steps that we're going to do with this. I've specified where I want that point to be and the directions of the third in the fixed. So I know where I want that body to be. And the first thing we did is, we took the tool point stuff and got 3's origin. So, okay, so step 1. Because now I know that 3 to fixed, what I want that to be. Made a couple of free choices to establish the S4. The names have changed. So the S4 turns out to be the negative of the y-axis. As I'm looking at this, I think I've got my S4 the wrong way today. Maybe the negative. Oh, and wait a second. X. Oh, no, we're okay. If that was the X and that was the Y of the third, X cross Y would give me, so I do have it in the negative of the Y. Okay, based on those choices. So now there's this line. I know it goes through that point, and I know its direction. I know that all in the fixed, and there's this line. We're going to get the unique perpendicular between those. So at least to close the loop is not anything different. We're going to close the loop and say, what do we get? 3 distances. That. Oh. When we close the loop, we start here, and we walked there, and then we walked along S4, and then here was the unique perpendicular, and then we walked back here. So I have a new thing. When I close the loop, I'm going to get that distance. So boy, I got another weird thing, happening on this because of the cylindric at the beginning. When I close the loop, I'm going to know that. And then the angles, I know theta 4, I know alpha, and then I know the gamma. So how does this close the loop thing come into play? Because when we do the spherical, the spatial 4-bar that we're going to get out of this, we are going to solve for S1. The robot wants L1, but I know that. Oh, so the robot wants L1. Oops. So it turns out that the L1 that it's going to get is the S1 that we calculate minus S1 closed loop that came out of here. So it's kind of similar to what happened where the robot wanted phi1, and that turned out to be the angle theta 1 that came out of the analysis of the closed loop 4-bar minus the gamma that came out of the closed loop. So we got something, again, it's funky. For this to be the first problem, I didn't want to really introduce weird stuff. It was okay to do as the second or third one, maybe. Because, so hopefully I'm hoping that when you look at this, you're saying, oh yeah, because when I did the close the loop, I went here, I walked there, I walked there, I walked there, and I came back. So I am going to get that distance. When I do my analysis, I'm going to get that S1 distance, but what the robot wants is that. Oh, okay, I can use the S1 closed loop to convert it and to get it at the end. So once we close the loop then, I tried to say the salmon color thing is the stuff that never changed. Wasn't much there. The free choices that we made to get the S4 line, we made A340 and alpha 3490. And then when we close the loop, we got three distances, that, and that, and three angles, that, and that. Finally, we got a simple 4-bar, which is what I thought would be the simplest one to show for the first one, but then I had those terrible stories. Oh, so for the simple 4-bar, if I go, what are my unknowns? Theta 1, 2, and 3, and then I also need the S1, S2, and S3. But we get the angles first because it decouples. So Z41 equals C23. That's going to go to A cosine plus B sine plus D equals 0. Pretty easy. And then I looked at the buddy equations, X and Y for 1. Okay, it's going to be a fundamental. Oh yeah, they're fundamentals. That's nice. 4-1 is going to be 2, 2, 3. So we're going to take the A case of theta 1, solve for the sine and cosine, the A case of theta 2, and then the B case of theta 1. Boom. And then I'll look at these. Again, I don't have to use these buddy equations, but they have just never failed. So I'm like, what the heck? Turns out they're fundamentals. 1, 4 is going to be 3, 2, 3. Again, I'll take theta 1A. I know theta 3A case. Theta 1B. And then, how am I going to get this for the A and the B case? Well, I'm going to go ahead and write the vector loop equation. And there's only 8 terms because it's a 4-bar, right? There's 4 of the S vectors, and I can, and again, engineering essay question, I can take, because I know for the A and the B case, all the angles, I can evaluate all 8 of those vectors in a common coordinate system for the A case and solve 3 equations in these 3 unknowns. And then evaluate all those vectors for the B angles. So because the equivalent spherical was a 4-bar, I was all excited. Said, well, I'm going to go with this because it's the simplest one. But then you had the crazy stories because then at the end, when I do calculate my A and B case of S1, the robot wants, the A case of L1. So that's going to be S1 A case minus S1 closed loop. And L1 B case is going to be the B case value of S1 minus S1 closed loop. And of course, phi1 for the A case is going to be theta 1 A case minus the gamma that we got when we closed the loop. Oops. And phi1, boy, my writing is getting really bad. Phi1 B case is theta 1 B case minus the gamma. So weird stories because we really had to be careful when we closed the loop that this is the value that's going to come out. Because we went here, walked, 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 walked. Yeah, that's the value. But I like the picture, so hopefully the picture made it clear. But for the first one, and that's the first one, the first reverse analysis we do, I didn't want there to be weird stuff pop in, and weird stuff popped in. Now, and this talked about how to write the vector loop and I do have a numerical example in the book, so I guess it's okay. So here's my constant parameters. This is what I picked for all of these vectors, position, orientation. I got 3's origin and made those choices. I closed the loop, got all that. And, whoops. Then, again, those were constants. Free choices have 1 asterisk. Double asterisk was the close the loop. I just want to indicate that for the 4-bar, we knew all the A's and all the alphas, and I knew, oops, and I knew that guy. Okay, I was kind of staring at that, so yeah, that's okay, right? I know that theta 4, so we can solve the 4-bar. And it would have been neat if I would have, there's nothing new here. This is just the talking story. Yep. And again, how we got the parameters the robot wanted, but when we solved the 4-bar, we were getting the A and the B case of those parameters. So when I get down here and I do that, I say, wow, okay, we're done with chapter 7. So I'm hoping you feel okay. I would have been happier today if I didn't make that typo on that exam that we just looked at. Because you go back and you say, you study, you assume that whoever wrote that knew what they were doing, right? I cut and paste from a previous year where they only had 5 elements. So what we're going to do next, so this will be in the next video, is we're going to look at, say a mechanism like this. I'm trying to think of how we're going to change this. Basically, what we're going to do in the next chapter is we're going to look at a closed loop mechanism that has mobility equals 1, but when we go ahead and generate the equivalent spherical mechanism, it's going to have mobility 2. So that's the group 2s. And there's a lot of neat stuff in that chapter. I really like the chapter. You're going to see some weird stuff up here, but I really like the chapter. Because what happens is when you analyze the spherical mechanism over here, because it's 2 degrees of freedom, what's going to happen to us is when we go into our toolbox, the best I can do is to find 1 equation and 2 unknowns. So we're like, right? So the problem's not going to decouple. So that means I need to get a second equation in those 2 unknowns, and I'm going to have to get that equation from the 3D mechanism. Oh, so now those equations are going to have joint offsets, the S's, and link lengths, the A's, right? None of these equations had any of that. Life was great when we were over there. But that's what's going to happen because the 1 degree of freedom spatial, because it's equivalent spherical, is 2 degrees of freedom. Again, in the toolbox, the best we can do is 1 equation and 2 unknowns. So we're going to have to go over here and find another equation in those same 2 unknowns. And then we have to figure out how to solve that and do all that stuff. So it's more challenging, but I really like them. The group 3s and 4s, they were people's PhD dissertations, so we are not going to expect you, again, on a test to solve a group 3. We're going to look at it from the point of view, hey, that's interesting. If I ever run into one of these, I might open the book to that chapter and see how they did that, just as a reference. Okay. Oh, so again, Friday, I'm going to make a video tomorrow and then just post it for Friday's stuff. But yeah.
For the test question you showed us, like the first one today, how do you find the degree of freedom for the spherical mechanism?
Oh, when you go to the spherical, let's see, let me pop that one up to make sure I'm talking about the right thing. Oh, here it is still. So this was the planar representation of the 3D. So if I was to draw the planar representation of the equivalent spherical, I'd say, yep, I got a revolute, I got a revolute. Oh, the prismatic, boom, I know that one. I got a revolute. Oh, I got a prismatic, so I know that joint. Oh, and the cylindric gets mapped as a revolute. So for the equivalent spherical, the mobility equation for the closed loop mechanism reduced to the sum of the freedoms of the movable joints minus 3. So because I know those joint angles on 2 of them, there were only 4 movable joints, so 4 minus 3. Yep. Yep. And again, if I gave you one where the 3D had mobility 1, and I better give you one where that happens, or else we're in the wrong chapter on the test. So, but that's what happened. That's how I do that one. Okie doke. So I'll see you live on Monday, but you'll see me in the video world for Friday.